Hello my dear students. So I'm going to continue the lesson work, energy and power. In the previous chapters we discussed what work is. What is work done? When you apply a force, if the shape changes or if there is a change in position of the object, then we say there is work done by the object. So how did we calculate work? Work is equal to magnitude of force multiplied by the displacement of the force or the distance moved by the object in the direction of the force. And work is in the units joules. Thereafter we discussed energy. What is energy? The ability to do work. That is also given the standard unit joules. And under energy we discussed two types of energy. You all know them. Kinetic energy and potential energy. Kinetic energy is the energy possessed by an object due to its motion. When an object is moving, it has a velocity. Because of velocity, it has kinetic energy. And that is given by the equation half mv square. Then we discuss potential energy. What is potential energy? The energy possessed by an object due to its position or else the shape. So based on that, we were able to calculate potential energy using the equation potential energy equals mgh. M is the mass of the object, g is gravitational acceleration and h is the height at which the object is or the height to which the object is lifted. And there we said the work is done against the gravitational pull. So because of that, we call that potential energy as the gravitational potential energy. What was the next type? The elastic potential energy. When you stretch a spring, an elastic or a rubber band, due to that stretching, there is work done. And due to that, there is the energy stored that is known as the elastic potential energy. Then we looked at few examples. And I told you all, I will discuss the instances where potential energy is used in daily life. We did discuss some examples before also. Fruit falling from a tree, if you lift an object to a higher level and drop it, what will happen? Similar to that, there are more instances where potential energy is used in daily life. The first one. Water stored in high reservoirs is allowed to fall down to a lower level, transforming the initial potential energy of the water into kinetic energy. And this kinetic energy of the falling water is used to rotate a turbine to generate electricity. So what is this related to? The hydropower plant, where they use flowing water to generate electricity. So the water, you know, the waterfall. Normally from a higher level, the water flows down. So the higher the reservoir is or higher the storage of water is, there's more height. Because of that, the water will have more potential energy. And you all know, energy is transformed from one form to the other. Potential energy to kinetic energy, kinetic to potential energy. So here we will look at that energy conversion. Now look at the diagram. Here you can see reservoir. What is a reservoir? A place where the water is stored. Normally they go along with the geographical location. In addition to that, they build the dam and they store the water. So that becomes the reservoir. And usually the reservoir is at a higher level. So there you can see high reservoirs. These are the important terms. Water is stored in high reservoirs and it is allowed to fall down to a lower level. And there, the potential energy is transformed into kinetic energy. That is the important thing. So here you can see reservoir at a higher level. Higher level. If the height increases further, the potential energy that is stored in water will increase further. So here it is going to be the potential energy of water. Then what can you see here? The water flowing down. So when it flows down, what will happen to energy? There is velocity. So because of that, the potential energy will be converted to kinetic energy. So at this point, the potential energy will be converted to kinetic energy. Students, here I am using PE for potential energy, KE for kinetic energy. That is not the normal symbol that we use. This is just for you all to understand. I will give you all the explanation below. Then what happens here? You can see the turbine there. When the water falls down with a high kinetic energy, that energy is used to rotate the turbine. So there, the turbine starts to rotate. Because of the rotation, turbine has kinetic energy. Then what happens? From that kinetic energy, electric energy is produced. Electricity is produced. So here this part you all can see electricity being produced. And there in the power plant, electricity is stored and thereafter it can be distributed. So what is the energy conversion taking place here? Initially we have potential energy of water at a higher level. Then when water flows, the potential energy of water is converted to kinetic energy of flowing water. Thereafter, the turbine rotates and there it is the kinetic energy of turbine. And finally, when electricity is produced here, electricity is produced. When electricity is produced, it becomes electric energy. So there is energy transformation from one form to the other. Potential energy is used to generate electricity. So if we write down the energy conversion, we can say potential energy, energy of stored water, or we can even just say water, that is converted to what? Kinetic energy, energy of flowing water. Here again I am using the term stored water and flowing water to make it more clear, but you can just say potential energy of water, kinetic energy of water. That is also sufficient. Then, what is the next one? It becomes kinetic energy of turbine. When water falls on the turbine, turbine starts to rotate. And from that, electric energy is produced. Electric energy is produced. So there are these energy transformations. Potential energy of stored water becomes kinetic energy of flowing water. Then it becomes the kinetic energy of turbine. And from there, electric energy is produced. That is, electricity is produced. So this is what you need to remember, students. If they show you a position and ask you for the energy conversion, you should know to identify that. And you all have to remember, the higher the reservoir is, there will be more potential energy. Then that will be converted to more kinetic energy, and that can lead to generation of electricity more efficiently. That is what happens in the hydropower plant. So here again, you can identify the different energy conversions. From here to here, potential energy to kinetic energy. Here, kinetic energy, but kinetic energy of water becomes or is given to the turbine. So it becomes the kinetic energy of turbine. Then from kinetic energy of turbine, you get the electric energy. I'm sure you all can understand that clearly. So with that, students, I'll move on to the next example. Again, instances where potential energy is used in daily life. This is the second example, pile and tower. Look at the picture. You would have seen this in construction sites. Pile and the tower. Here you can see this is the pile. With that, there is a tower that is used to lift the pile up. Now, this is when they are putting up very tall, huge buildings. They need to have a very strong foundation. So, the soil has to withstand, the ground has to withstand that heavy weight. To do that, they dig and they put piles into the ground so that it provides a very strong support. So, to insert those piles into the soil, now here you can see the ground level, the pile has to go in. So, you can't just push it in or you can't just grind it and rotate it into it. You have to push it with a force or push it with a high energy. To do that, what they do is they lift the pile up and then they push the pile into the ground. So, the higher they lift it, the pile will get more potential energy. And when it is dropped down, it will go down with high kinetic energy. Because of that, it can go easily into the ground. Do you all understand that? If we look at this picture again, here the crane is used to lift the pile up. Here you can see there is a tower. That is the pile that has to be sent into the ground. So, they lift the pile up as much as possible. Here also you can see the crane lifting the pile up and then the pile is dropped down. So, it goes up, it gains potential energy. Then when it is dropped down, the potential energy is converted to kinetic energy. If we read the explanation, pile is used to tighten the loose soil in construction sites before laying the foundation of buildings. So, this is to tighten the loose soil. Like I said, to provide a strong foundation. This is done by lifting the pile to some height and releasing it to fall down to the ground below. So, when it is raised to a height, it is the potential energy, and when it falls down, it becomes kinetic energy. So, the height provides more energy for the pile to come down so that it can go into the soil easily. It can go into the ground easily. Is that clear, student? So, that is another example where there is energy conversion. So, here also potential energy, E potential, is converted to E kinetic. Potential energy is converted to kinetic energy. That is the energy conversion occurring here. I am sure that is clear to you all. So, we will move on to the next example. Instances where potential energy is used in daily life. The third one, sledgehammer. You all would have seen this sledgehammer being used. What is a sledgehammer and why do we use it? Now, here you can see there is a large log of wood. It has to be split into splints. To do that, what they do is they use a wedge here. You keep the wedge there and you hammer it with the sledgehammer. So, that splits the log into smaller splints. And when they do that, what do they do? Now, the sledgehammer is here. They raise it to a height. Usually, they raise it to a height above their head normally. So, then what happens? When it is raised to a height, it gains potential energy. And when it is hammered onto the wedge, what will happen? That potential energy will be converted back to kinetic energy. So, when it is raised from here to here, the potential energy is stored. And when that comes back down and hits the wedge, the potential energy is converted to kinetic energy. So, here also there is an energy conversion from potential energy to kinetic energy. And when you raise it to a height, there is more potential energy stored. You can start heating from here, only this much height. So the potential energy is less compared to this height. So if you raise it to a higher level, the sledgehammer gets more potential energy. That will be converted to more kinetic energy that will make work easy. So that is the purpose of using sledgehammers. In breaking stones and cutting firewood, sledgehammer is used. When cutting wood, an iron wedge is inserted into the piece of wood to be cut and the lifted sledgehammer is released on the wedge. That is important. So here what happens? You can see iron wedge is used and the lifted sledgehammer is released onto the wedge. The potential energy of the sledgehammer at the point of release transforms into kinetic energy, whereby it collides on the wedge with a larger velocity. That is the important part that I explained to you all. This part. I will read it again for you all. So there you can see the potential energy of the sledgehammer at the point of release transforms into kinetic energy, whereby it collides on the wedge with a larger velocity. The kinetic energy of the sledgehammer gets transferred to the wedge, which passes through the piece of wood, separating it into pieces. So again, conversion of energy or transformation of energy. Initially, you lift the hammer, so while it is moving, it's going to be kinetic energy. Once it reaches this point, it's going to be potential energy. And when it comes down, it's going to be converted to transformed into kinetic energy. And that kinetic energy will be given to this wedge. This is the wedge there. This is the wedge. So wedge goes into the log of wood with a higher velocity, with high energy. That splits the log into many splints. Is that clear to you? So again, related to conversion of energy or transformation of energy from one form to the other form. So that is another example for an instance where potential energy is used in daily life. So like this, students, you all can think of many different examples where we use potential energy, where we raise things to a height and release it so that we can gain more energy. And other instances where objects get potential energy and kinetic energy. Can you all think of another example? Now we have discussed this before also in one of your previous lessons. When you throw something up, an object is projected upwards. When you do that, you throw it up with a velocity. So initially there will be kinetic energy. But when it goes to a height, due to the gravitational pull downwards, you all know that the velocity decreases and at the maximum height, velocity becomes 0. But then what will happen? At the maximum height, the object will have potential energy. And then it comes down due to again gravitational acceleration. So there the potential energy stored in that object will be converted to kinetic energy. Say for example, when a batsman hits a ball and the ball goes up and when it reaches the maximum height, the velocity is 0, kinetic energy is 0, but the potential energy of the ball will be very high or maximum. And when it starts falling down again, the potential energy will be converted to kinetic energy. And if a fielder catches that ball, he will be catching a ball that has high amount of kinetic energy. Why? The potential energy will be converted to kinetic energy. I am sure you all have observed this before. So there is a conversion between kinetic energy to potential energy, then potential energy to kinetic energy. So like that, you all can relate many of the day-to-day examples with kinetic and potential energy. So with that, students, I have completed this topic, that is energy. Under energy, we discuss kinetic energy, potential energy, and the different types of potential energy as well as these examples. Now, I'm going to move on to the next topic, that is power. Power. When you say power, now you might have even heard the term horsepower. Usually they say out of animals, horses have very high power because they can run fast. That's why earlier in the ancient days, they used the unit horsepower. But now we use the unit watts. You would have seen that in electric appliances, household appliances, that is the power related to those appliances. But here we are discussing power related to work done. Now work can be done, the same amount of work can be done in different time durations. If you can do that work fast, then that means that object or the work done, power related to that work done is higher. If it takes a longer time, then of course the power will be less. So what is power? How fast you can do work, or the work done in a unit time is defined as power. Work done in a unit time. Or else you can say the rate at which the work is done is power. So you can define power in two ways. The work done in a unit time or the rate at which work is done. Both are the same things, and that is what power is. So if we define power first, power, the amount of work done in a unit time is known as power. Same way, we can say the rate at which work is done is known as power. So you all can use one of the two definitions. The amount of work done in a unit time is known as power, or else you can say the rate at which work is done is known as power. So as an example, we will consider this example given in your textbook. If 600 joules of work is done in 10 seconds, if we are to calculate power, now we can say power is equal to work done, that is going to be in joules, and divided by time taken, that is going to be in seconds. So what is the unit of power? Joules divided by seconds. This will have the unit joule per second. Joule you all know because it's the name of a scientist, Prescott Joules. It has to be capital J, then seconds, joule second minus 1 joules per second. But this unit is equal to watts, capital W. Again, that is watts. That is the standard unit of power. So here, you have to remember these, students. And this is the SI unit. So power is given by the equation work done, that is in joules, time taken in seconds. So when you divide joules by second, joule per second, that is equal to watts. Watts is the SI unit of power. So here, if we are to calculate the work done, in a unit time. That is power. So there power equals work done divided by time. When you write the equation, students, you can even write work divided by time. So that is going to be 600 joules of work in how many seconds? 10 seconds divided by 10 seconds. So that will be equal to 60 joule second minus 1, and that's going to be 60 watts. Is that okay? So the power at which the work is done is 60 watts. That means 60 joules of work is done in a unit time. I'm sure you all can understand that calculation. So if I quickly go back, power, the amount of work done in a unit time, is known as power. The rate at which work is done is known as power. So as an example, if we take, if 600 joules of work is done in 10 seconds, how we calculate power? So this is the equation. You all have to remember that. So when we are calculating power, power equals work done divided by time taken. So 600 joules divided by 10 seconds, that will give you all 60 joules per second. And that's going to be 60 watts. Is that clear, student? I'm sure you all can understand that. With that, we'll move on to the next slide. So 1 joule per second, that is 1 Js minus 1. Students, there is a mistake. That is actually a printing error in your textbook also. When we write standard units, you all know seconds have to have simple s. Seconds is written as simple s, not capital S. And always between two units, you need to have a space. So this should be joule second minus 1. 1 joule second minus 1. That is how we are supposed to write. So 1 joule per second is defined as watt. That is 1 watt. Hence, the power indicated above is 60 watts. That is, the unit of power is watt. The following equation is used to calculate the power. I have already introduced this equation to you all when we did the calculation. So, the equation used to calculate power is equal to work done, that is going to be in joules, divided by time taken, that is in seconds. So if you divide it, you will have the unit joule per second, that is equal to watts. So 1 joule per second will be equal to 1 watt. That is the SI unit of power. So you have to remember that. Here is defined as watt, and hence the power indicated above is 60 watt. That is, the unit of power is watts. That's what you have to remember there. SI unit of power is watts. Is that clear to you all? So then I will move on to the next slide. Example. The time taken to lift a mass of 5 kg to a height of 8 meters is 10 seconds. Calculate the rate of doing work, that is power. So what is happening here? There is a mass here that is being lifted to a height. So what is the height from here to here? Now let's say this has a mass of 5 kg. And we are lifting it to a height of 8 meters. And for that, it takes 10 seconds. So how are we doing work here? You can remember, students, the object is there. You are lifting it against the gravity. So what will happen when you do work? That will be stored as the gravitational potential energy in the object. So that is the work done. How do we calculate that? You know the equation. You all know how we come to that. Now here mass is given to us. So let's say mass of the object, that is 50, that is 5 kilogram. So what is the weight of the object? Weight of object. What is the equation we use? W equals mg. You can remember that. M is mass, g is gravitational acceleration. So that is 5 kilogram into 10 meters per second square, gravitational acceleration. So if we write the weight of the object, that is going to be 50 Newton. So what is the force needed to lift the object? The same as weight, that is 50 Newton. So here force needed to lift the object, that is going to be 50 Newton. So when it is lifted to a height, so here height lifted, what is that? 8 meters. So what is the work done? Work done is what? Force into height. So there it's going to be force into height. That is going to be 50 Newton into 8 meters. So there it's going to be 400 joules. 400 joules. Then what is the power? Work done in a unit time. So here if we say power work done divided by time. So we have calculated the work done. 400 joules. 400 joules. What was the time taken? It is 10 seconds. So divided by 10 seconds. That's going to be 40 joule per second. And if you write the answer, it will be 40 watts. That is the power with which the work is done. Is that clear to you all? If we look at the example again, the time taken to lift a mass of 5 kilogram to a height of 8 meters is 10 seconds. I have shown everything in the diagram. You all can see here. 5 kilogram mass that is lifted to a height of 8 meters. It takes 10 seconds. So calculate the rate of doing work, that is power. To do that, what do we need to do? We need to calculate the weight of the object and we need to find the work done. So mass of the object is 5 kilogram. Weight of the object is mg. W equals mg. So we multiply 5 kilograms by gravitational acceleration 10 meters per second square. So you get the answer as 50 Newton. Then in order to lift the object up, we need to apply a force. And that force should be equal to the weight of the object. Force needed to lift the object is going to be 50 Newton. And the height to which the object is lifted is 8 meters. So the work done is going to be the magnitude of force multiplied by the distance moved by the object. So here the distance moved is the height. So force into height. 50 Newton into 8 meters. You get the answer as 400 joules. So thereafter, if we calculate power, power is work done divided by time. So 400 joules divided by 10 seconds. That is 40 joules per second. And the answer is 40 watts. So watts is the standard unit of power. I am sure you all can understand this calculation easily. So with that, students, I will move on to the next slide. So example 2. What is the work done in a minute by a machine operating with a power output of 100 watts? So here they have given you some values. Power is given to you. Power equals 100 watts. That is the work done in a unit time. So work done in a unit time is equal to 100 watts. When we say unit time, what is the unit time here? Work done in 1 second. So here this is 1 second. What is the time duration they have given? Now here you can see time is given as in a minute. That is 1 minute. Now what is the unit did we use for time? Their time has to be in seconds. But here time is given as 1 minute. And 1 minute is equal to 60 seconds. So what do we need to calculate? What is the work done in a minute by a machine operating with a power output of 100 watts? So the machine has a power output of 100 watts. We need to calculate the work done in a minute. So that means we need to calculate the work done in 60 seconds. So if we use the equation for power, what is power? Work divided by time. Earlier also I told you all students, you can write it as work done, time taken, or simply you can write it as work divided by time. Now we need to find work. So we need to rearrange the equation. How do we do that? We can say work done in 60 seconds. That is equal to what? Power into time. So you rearrange work done in 60 seconds equals power into time. So power is given to us as 100 watts into time is 60 seconds. Now here you all know, students, 100 watts means 100 joules per second into 60 seconds. So when you multiply 100 into 60, 6000 joule per second into second, you get the answer, the unit in joules. So that is work done. The work done in 60 seconds is 6000 joules. So I'm sure you all can understand this calculation also. If we quickly go back and look at it. Example 2, what is the work done in a minute by a machine operating with a power output of 1000 watts? Power is equal to 1000 watts. Work done in a unit time, that is 1 second, is equal to 1000 watts. So here work done in a unit time, that is power, that is 100 watts. You can also write it as 100 joules per second. Time is given to us as 1 minute and we need to convert it to seconds. So it becomes 60 seconds. Then if we calculate power, power is equal to work over time. You need to rearrange it so that we can calculate the work done in 60 seconds. So work done in 60 seconds should be equal to power multiplied by time. So if we do the calculation, power is 100 watts, 60 seconds, or since you know the conversion, unit conversion, you can skip the first step and write the second step directly. Either way is fine. 100 joules per second. So that is into time 60 seconds. That will give you the work done in 60 seconds. That is work done in 1 minute, 6000 joules. So if you want, finally you can write it also. work done in 1 minute is equal to 6,000 joules. So that is how we do the calculation. I am sure students, you all can understand this very clearly. With that, I will move on to the next slide. I will give you all an example. Now let's say an object has a mass of 4 kilogram. It was lifted to a height of 5 meters in 10 seconds. Here I am going to summarize and combine all the calculations that we have done. So in this, now if you show it as a diagrammatic form, this is the object here. It is lifted to a certain height and the height is going to be this. What is the mass of the object? 4 kilogram. What is the height? It is 5 meters. And for this to happen, it takes 10 seconds. Now here you all know students, initially the object is here. I will mark this as position 1 and we'll say this is position 2. So here, when the object is here, it's going to be at rest. There's no movement. But when you are lifting it up, you are going to do work. So you all know how to calculate the work done. How do we do that? We need to calculate the potential energy gained by the object. So first we can find the potential energy gained by the object. What is potential energy? E potential is equal to mgh. So if you use this equation, m is 4 kilogram, g 10 meters per second squared, and height is 5 meters. 5 meters. So if you multiply that, 4 into 10, 40, 40 into 5, 200. What is the unit? Potential energy, joules. Then, if you are to calculate the work done by lifting the object, what is that equal to? Work done is what is converted to potential energy. So work done by lifting the object is equal to the potential energy gained by the object. So that is going to be again equal to 200 joules. Is that okay? Then, the next one. If we are to calculate the power is what? Work divided by time. What is work? That is 200 joules. How long does it take to do the work? I have given you the time here. It takes 10 seconds. So then, 10 seconds. So that is going to be 20 watts of power. Now we have included work, potential energy and power. What is missing there? Kinetic energy. How can that be related here? Let's say the fourth one. The object was released from the height to fall down to the ground. Find the kinetic energy of the object when it reaches the ground. So what will happen there? Now the object is here and it is going to come down. It is going to come down. If we again look at the values, you can remember 4 kilogram, 5 meter height, and it took 10 seconds. And we calculated potential energy as 200 joules. So this is a 4 meter height. E potential was calculated as 200 joules and it takes 10 seconds for the object to come down. So when it reaches its original position, that is the ground again, there what will happen? Here it is E potential. You all can remember, students, the velocity will be 0. Therefore, E kinetic is going to be 0. When the object goes to the maximum height, it is not moving. So, there is no velocity, there is no kinetic energy. You can remember the example where we looked at a fruit falling from a tree. So, you all know that. We discussed about energy being converted. When it comes down, what will happen? This potential energy will be converted to kinetic energy. So here it will be E potential will be 0, but E kinetic will be equal to this 200 joules. Is that clear to you all? So kinetic energy when the object reaches the ground is going to be 200 joules. So kinetic energy when the object reaches the ground equals potential energy at a height of, the height is 4 meters. So that is equal to the same value 200 joules. So that is how, students, you all can relate all the quantities that we discussed now. We started with work, then energy, and energy, potential energy and kinetic energy, and then power. And here I did it in a different order. Normally you can calculate work first and then find potential energy also. So if you are to find work done first, what do? We know the mass. I will go back to the example and explain it there. So here, without calculating potential energy, if you are going to calculate work done, you can see here, you know the mass of the object, you need to find the weight of the object, 4 into 10, 40 Newton, and you need to supply that amount of force to lift the object to a height. So 40 Newton needs to be applied, and when you lift it to a height, magnitude of force into the distance moved by the object is going to be the work done. So 40 Newton into height 5 meters. So that is also going to be 200 joules. Either way, it's the same calculation. So you can calculate potential energy first and then you can calculate work done, or you can calculate work done first and that will be equal to potential energy. So then, if the object falls down, that potential energy will become kinetic energy. Thereafter, students, you all know the equation for kinetic energy. They can ask you to calculate the velocity of the object when it falls to the ground as well. So that also can be included in the question. So all these are calculations related to work, energy and power. I'm sure you all can understand that. So with that, students, I have come to the end of the lesson. I have discussed all the concepts with you all. In the next slide, I will discuss the summary of this lesson with you. Summary. The work done by a force is equal to the product of the magnitude of the force and the displacement along the direction of the force. So this is the equation that we used. The work done by a force is equal to the product of the magnitude of the force and the displacement along the direction of the force. So that is, here it is given to you, magnitude of the force into distance moved in the direction of the force. So instead of distance moved in the direction of the force, we say displacement of the force or displacement of the object. And if it is being lifted up, we say the height lifted. So either way, it is going to be the distance moved in the direction of the force. Then, if there is no energy loss, the work done is equal to the energy expended. So when we did the calculation, students, even in the previous slide, I said the potential energy gained is equal to work done. That is considering there is no energy loss. Normally, there will be energy loss, but we consider when we do these calculations that there is no energy loss. That's very important. If there is no energy loss, then the work done will be converted to the energy expended. The unit of measuring work and energy is joules. Both are joules. The standard unit of energy and work done are joules. The two forms of mechanical energy are the potential energy and the kinetic energy. So that is the next one, two types of energy. What is kinetic energy? Energy possessed by an object due to its velocity or due to its motion. Energy possessed by an object that is in motion. So the kinetic energy of an object, it depends on mass and velocity. If the object is heavier, the mass is higher, the kinetic energy is higher. If the object is moving with higher velocity, then also the kinetic energy is high. So the kinetic energy of an object depends on its mass and velocity. This is the next point. And the kinetic energy is calculated using the following equation. So that is again something that you have discussed. Kinetic energy, normally we write it as E subscript K half mv square, where m is the mass in kilograms and v is velocity meters per second. That is very important. That is an equation that you all have to remember, students. Calculating kinetic energy. Kinetic energy half mv squared, where m is mass and velocity v. And the standard units. Mass has to be in kilograms. V has to be, velocity has to be in meters per second. So you will get the unit for kinetic energy as joules. There are three factors that affect the gravitational potential energy. What are they? Mass, m, that also should be in kilograms. That should be in kilograms. Gravitational acceleration, 10 meters per second squared. And height, it should be in meters. You all know, students, gravitational acceleration, the exact value is 9.8 meters per second squared. But for calculations, we take it as 10 meters per second square. So from that we build the equation. What is it? Potential energy is equal to mgh. I will move on to the next slide. So the following equation is used to calculate the gravitational potential energy. This is the equation. What is it? Gravitational potential energy is equal to mgh. Mass into gravitational acceleration into height. Then, the potential energy of an object changes when its shape changes. So, for that also we looked at many examples. What are they? When you stretch a string, when you stretch a rubber band, when you stretch an elastic, or I told you all when you use a whining toy, when you rotate it and when you rotate the key and the coil gets tightened, then also there is potential energy stored. That is known as the elastic potential energy. That can be related to the catapult, even bow and arrow. You pull the bow with the arrow, so there is elasticity. With that elasticity, there will be potential energy gained by the bow, and when it is released, that potential energy will be converted to kinetic energy, which gives a higher velocity for the bow arrow to travel forward. So there is energy conversion. Even catapult, when you pull the rubber band, elastic band with the stone, when you pull it back, there is potential energy gain, elastic potential energy. And when the stone is released, the elastic potential energy that is given to the stone will be converted to kinetic energy. So the stone will move forward with a velocity. So there we use potential energy. In addition to that, we have discussed many examples where in day-to-day life we use instances where potential energy is utilized. So there, when an object moves upwards under gravity, there is a loss in its kinetic energy, and this lost kinetic energy is transformed into potential energy. So that is the energy conversion. When you are moving an object up, velocity decreases, so kinetic energy is lost. Then that kinetic energy is transformed into potential energy. And at the maximum height, it is the maximum potential energy. And when the object comes down again, that potential energy is in turn converted to kinetic energy. So at the lower level, where there is velocity, it will be kinetic energy. At the higher level, where there is no velocity, velocity 0, but due to the height, the kinetic energy will be converted to potential energy. Again, when the object comes down, it's going to be kinetic energy. So that can be related to reservoirs, where water is stored in hydropower plants, then the sledgehammer. All these are different examples. Pile towers, all these are examples where this energy transformation takes place. So after that, we discuss power as well. Work done in a unit time. So with that, students, I have completed this lesson. So I am sure now you all have a very good understanding as to what work, energy and power are. So with that, I will end this chapter, and in the next chapter, I will start discussing the miscellaneous exercise given in your textbook, and thereafter I will discuss some extra questions. I am sure you will answer those questions first by yourself, and then you can listen to my discussion.